Yeah.
All right.
You can record now, right?
Yep. Okay, and then
Good.
now you're back to host.
Okay. Okay. I wanted to show you something. Like for example, you've heard about divide and conquer method in any of the algorithms. Maybe we are looking at merge sort or quick sort. All right.
Yes. So I haven't done those. I haven't done the sorts yet though. I'm not able to implement them yet.
Okay. Okay. Let's look at something. For example, you have an array, or you have an array. You have the items in the array 1. You have like, okay, you just have numbers. Oh, pardon me, I'm now separating with commas. Hope you can see, right?
Yep, I can see it.
Okay. Okay. For instance, you have this length of array that is 6. Okay. Hello.
Yep, I can hear you.
Okay. When you have an unsorted array, okay, and you first of all you actually want to scale it down instead of from O of n to log n. You need to first of all sort it. Okay.
Okay.
And there are so many certain algorithms, like you have merge sort, quick sort, although you still have other types like bubble sort, insertion sort, selection sort, but those ones, because of the big O analysis, they are not good, so to say. They are not efficient to sort arrays because they sort at arrays at O of n squared. So which makes them not to be efficient. So the ones that you need basically are quick sort and merge sort for you to sort via arrays. Now, when you have sorted this array to 1, 2, 4, then 10. I'm just trying to make an explanation. All right.
Right. Yeah.
Okay. Then 17. Then, okay, 50. Assuming that the arrays were not sorted from the onset, all right? You need to first of all sort them out, okay?
Right. So
when you have sorted
saying
them,
the one on the left should have been unsorted. Is that what you mean?
No, yes, it should have been unsorted. The
Okay.
one on the left-hand side should have been unsorted, okay?
Right, gotcha.
Now, after you've implemented like any of the sorting arrays for it to become the one on the right side that's sorted. Right. Now, if you are going to iterate from index 0 to the array length -1, right. Okay? You know, it's like you're iterating through an array. So it's going to be, the big O notation is going to be at O of n, all right? Okay. Now, for you to actually scale this down from O of n down to log n, you can implement divide and conquer method, all right? Oh, sorry, binary search. Gotcha. Okay, and what binary search does is basically it employs divide and conquer method. Now, for example, if we are looking at 50, okay, if you want to get 50, if 50, it's actually what we are looking at. If we are using an array to iterate through it, you need to check with 1, that's at index 0, then 2, 4, 10, 17, 50. That's like 5 operations, okay? But with binary search, you just divide this array, find the middle point and divide it into 2. You now have, okay, 4 items by your left, and you can now have 3 items by your right. You now check in between now. Are you with me?
Yep.
Hello?
Yep, I'm still here.
You now check in between. Yeah, you now check in between. Remember, we are looking for the number 50, right?
Yep.
You now compare your 50 with the left-hand side of the array. 50 is still greater than it, but the right-hand side of the array, the last item, 73, it's bigger or greater than 50, all right? So you can discard this first portion.
Right.
Did you get that?
Yep.
Good. You are now left with 3 items on the right-hand side. And the 3 items now are 17, okay, 50, and 73. Oh, sorry, my bad. And 73, all right? Remember, what you're looking for is 50, okay? You come down in between again to check if 50 is greater than this middle item that is remaining from what we got from the right fragments of our array. You now find out that 50 is equal to 50. Is that true?
Yep.
The 50 that we are looking for is now equal to this 50. Now, what we have just done is 2 operations instead of 1 from the normal sorted array, instead of 1, 2, 3, 4, 5, 6.
Right.
All right? Good. So what we have just done now, we've just done 2 operations, which uses less memory and resources of the device for us to have done this least amount of operation instead of iterating through the array for us to have done 1, 2, 3, 4, 5, 6 iterations. We now scale it down from 6 down to 2. That's the first one, okay? Right. And now the second one, where we got the number 50. So right. This is how you, by implementation, you now scale it down, all right? From, let's go back to that chart. You now scale it down from O of n. Okay, sorry, the graph itself. From O of n, you now scale it down to O log n.
Right.
Does that make sense?
Yeah. Are you on the graphic right now? I'm still seeing the whiteboard.
No, I'm on the graph now.
Oh, okay.
Okay. Oh, sorry. Let me share the graph. Sorry.
Okay.
Sorry, I didn't share it. Okay. Okay. You can now see the graph, right?
Yep.
The big O, the graph. You now see that we have scaled it down from O of n down to O log n.
Gotcha.
All right. So we have been able to reduce the number of operations that should have been done at O of n, which should have been about 6 operations, and we've now brought it down to O log n, which just took us 2 operations. So that's how you scale it down from O log n to, sorry, from O of n to O log n.
Gotcha.
Yeah.
And that search, what search was that we did? Was it the, not binary search, was it?
Yeah.
No, binary, okay.
So okay, tell me which of the algorithms that you've actually like done that you have good grasp of.
Not many. I'm just starting for the most part.
Okay, like from the explanation that I just showed you, if you look at common data structures operation, okay, you now look at it, you now see binary search.
Yes.
Hmm?
Oh, log in. Yeah, that was what we just
when
saw.
you now look at binary, so does it now make sense that instead of using an array or O of n, you are now down at by implementing binary search tree, and you are now down, you've scaled it down from O of n to O log n.
Right. Absolutely.
Good. Good. So that's just the implementation. That's just the way you actually like make an application to become efficient.
Right.
Okay. Tell me, what do you know about basically about big O?
You said, what do I know about it?
Yeah.
So basically kind of
You told me that you've actually looked at it.
Yeah. So saying that to say, so I know of, like, for instance, with the different speeds. So even just so for instance, I know with O of 1 being the best, even with O log in, I had to double check, the cheat sheet to make sure which one that was. But saying that to say, I know that I think when it's when you do like two for loops, then it'll kind of like bump it up to I think even higher than O of n, right? Like if you got a nested for loop, then it'll like severely increase the time. But so saying that,
when you do two for loop, nested for loop is what?
I feel like it bumps up the the time complexity, but I'm not sure. I'm just trying to give you an idea where I'm at with it. So I have a loose understanding of it, but saying that to say that I know that it bumps up in the time complexity. Oh, what was that?
Okay. I think basically what you actually need first of all is to have a good grasp of big O, because when you look at this page that we're on now, okay, you look at data structures, you find out that big O is actually very, very important in measuring the efficiency of all these data structures, right?
Right.
Both the time complexity and the space complexity, right? Then when you scroll down, you also check the algorithms. You find out that of all the different types of algorithms, big O plays a very central role to compare their efficiencies, all right? So you find out that if you know the data structures and you know the algorithms, all the algorithms, and you don't know the big O, if you don't have a firm foundation in big O, it would be difficult for you to know your way around, to do some kind of trade-offs, all right?
Right.
As regards to time complexities and space complexities of different data structures and algorithms.
Right.
Okay. Hello?
Yes. Yep. I understand.
Yeah. So that's just basically, okay. If you wouldn't mind, let's go down to big O itself. All right. Let's start from big O.
Okay. Sounds good. And all of these algorithms here. Yeah. Can you hear me?
Okay.
Yeah, I was gonna say too, all of the algorithms, I haven't really implemented each. the quick sort, merge sort. I haven't implemented all of those yet.
Yeah. Okay,
So
no problem. I actually sent you a list of what I had intended us to do. You told me that okay, they are okay by you. Like I said, big O arrays, hash tables, linked lists, as in the singly and the doubly linked list, stacks and queues, trees, graphs, sorting, all the sorting algorithms, then the searching algorithms. That had been the other I had wanted us to follow because
yeah,
okay, let me tell you this.
yeah,
My
because
little
I had to
experience
learn all
was
that.
when I wanted to learn when I wanted to learn data structure and data structures and algorithms, I kept on running around, and with all those, it's very difficult, all those kind of testimonies and all that. So I couldn't get to know the right place to start from.
Right.
But it so happened that there was this course I actually took, and the tutor actually, the first thing that he actually thought was big O. And
Yes.
he began to teach about the different types of data structures. You now begin to see what those data structures are meant for and how big O plays a very important role in the implementation of all those data structures when it comes to different kinds of operations like the access, search, insertion, deletion operations you can do with each of the data structures. All right. So that was why I said, even before we actually started discussing, I said it's data structures and algorithm. For me, I can use an analogy of they are a building. All right.
Mhm.
Okay.
Yep.
But the foundation of both of them is the big O.
Yep. Makes sense.
As you can see from this big O cheatsheets.com where we are, you now see that all the data structures, all of them have their big O has its central role in all of them. When you also look at the algorithms, you actually find the same is applicable to, excuse me, the algorithms. So it's just to tell you that you cannot actually, or one can't, or shouldn't be good when it comes to this cost in quote without actually having a core understanding or concept about data structure, about big O.
Big on. Yep.
Okay. From there, you begin to build on top of the knowledge that you have acquired. All right.
Right. Understood.
Hello, Tony.
Yep. I understand. Can you hear me? Yep. I understand.
Okay, good. So that's why I said if you wouldn't mind, let's actually go through big O and look at exactly what it is. Okay.
Yep.
Okay. 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 First of all, let me ask you, do you know why, irrespective of the fact that you can use your device, your laptop, PC, whatever PC that you use, whether it's Mac or Windows operating system, do you know why you can't basically use your device to actually measure the speed or efficiency of your program?
Oh yeah, because
Hello?
yes, because basically your algorithm, it'll change depending on the resources that your device, from device to device. Is that what you mean?
Okay. Okay, that's one.
Um,
Any other reason?
Probably because some of the
Hello?
yeah, so I think because some of the memory will already be allocated.
Hello, Tony.
Yes,
Are you still there?
yeah, I'm still here. I'm still here. Can you hear me?
You said some of what?
Can you hear me?
Hello?
Hello, hello, hello. Can you hear me? Let's see.
Hello, Tony.
Yeah, can you hear me? Hello, hello, hello.
Yeah, I can hear you now. I wasn't hearing you.
Oh, okay. I don't.
Okay. Yes, I
Yeah.
can hear you now. Yes,
Okay.
yes, I can.
So what
Yeah,
was your?
I'm
Can
here.
you repeat your question that you say? What was your question that you said?
Okay. I said, do you know why it's why using your device to measure the efficiency of an algorithm is actually a okay, I said, do you know why using your device to measure the efficiency of data structures and algorithms is actually a bad idea? You've given me basically one major reason, and I'm still waiting whether you still know some other reasons.
Gotcha. Let's see. So yeah, so basically, depending on the device,
Hello?
yeah. Can you hear me? Hello, hello. Can you hear me?
Yes, I can.
Okay. So yeah, so depending on the
Yes, I can.
device.
I can hear you.
Oh, okay. Yeah, so the allocated memory, basically it will depend on, it'll change from device to device. And then also you can be using so much of your memory, I believe, on your device for other programs. But basically, I guess I would call it like different variables that would speed or slow up the device.
Okay. Yeah, simply put, the device could be performing some other tasks that could be consuming more memory than
Right.
than not okay, be using some other resources of the memory so that it will not be able to concentrate and only measure the performance of your algorithm, right?
Right. Right.
Hello?
Yep. Yep. That's correct.
Okay. Do you know of any other reason aside these two? Do you know do you know of any other reason aside these two?
Not that I can think of.
Okay. Okay, let me tell you.
Okay.
Most times a whole lot of tutors won't tell you actually the third reason. Some may mention it in passing, but won't like try to really explain it to you. The
Okay.
third other reason is, algorithm is independent of any language, right? You can
Right.
implement it using Java, C, any of the C's, JavaScript, Python, and all that, right?
Right. Right.
Now, when you actually look at the compilers, when you actually look at the compilers of all these programming languages, they have
Mhm.
different rates of performance. Okay,
Right.
that's why the C's are very fast programs.
Mhm.
You notice when you compare the C programs, the C compiler is very closer to low-level codes or languages that they can easily interpret any code that you've written in C for the machine to actually understand it and quickly respond or interpret it, so to say, to give you what you have actually coded. Unlike the
Right.
JVM, which is a compiler for Java code, is not as
Right.
fast as the C compilers. All right.
Yes.
When you actually look at when you compare, JavaScript is a just-in-time interpreter or compiler. That's the compiler for JavaScript, okay?
Right.
You find out that it was built in order to enhance performance of JVM, okay? So it's a little bit faster. So when you have written, when you have actually used different languages, sorry, to write the same algorithm, they will be interpreted at different rates. So this another third reason why, if an algorithm is written in C and you are trying to compare its efficiency with the same algorithm written in Java, you find out that that of C will be a bit faster than that of Java. So those are the reasons why using your device is not actually an efficient way of measuring the performance of all these algorithms.
Right.
Is that clear, right?
Oh yeah, yep, that makes sense.
Okay. It does, right?
Yep, that makes sense.
Okay. So because of these basic three reasons, because of these three basic reasons, why the one's device can't be used, because different devices have different rates at which they process data and all that, and the same device could be performing other tasks which will slow down its interpretation of your code and the different rates at which the compilers of different programming languages run at. Now, because of these three reasons, they have to come around to get, let me use the word standard, to measure the efficiency of an algorithm. And that was how Big O actually came to play a central role in measuring the performance. Now, when you talk about Big O, basically from the chat, I'm still on that website, bigocheatsheet.com. From this chart, you find out that we are just trying to measure the number of operations that is being measured per time as the input or the data increases, right? And tends towards infinity.
Right.
Is that correct?
Yep, that makes sense.
Hello?
Yep, that
Good.
makes sense. Yep. We've
Okay.
got a little bit of a delay.
Definition wise, hello?
Yep, I'm here.
Hello?
Yep, I'm here.
Okay, definition wise, let's look at what Wikipedia has to say about Big O. Wikipedia defines Big O as a mathematical notation that describes the limiting behavior. Note that phrase, or sorry, that clause, limiting behavior of a function when the argument tends towards a particular value or infinity. Now, simply put, the limiting behavior has to do with the large input of data that particular algorithm or data structure has to process. Like we just looked at an array and binary search tree. You actually see that as the number of inputs or the number of data increase, the efficiency of an array was actually slower, right? While that of binary search tree was faster when you compare it to that of an array.
Right.
Is that correct?
Yep, that's correct.
Okay, good. So that's basically what Big O is actually a measuring tool to determine the scalability of a code. Let me use that word, or of a program, and the overall of an application, because all these programs or codes, they actually make up an application. Okay. Right. Now, basically, we've established that big O measures the number of operations as the inputs of the data increase, right?
Right.
Hello?
Yep, that's correct.
Okay. Now, when you want to measure big O, there are some kind of rules that you can apply that will help you to actually determine at which efficiency will the data structure or the algorithm run, whether it's going to be at O of n or n log n or O of 1 or the or quadratic. That's O n squared and all that. So, or even the factorial, which is at O of n factorial. Now, the way you actually determine it, it's okay. Let me actually go to VS Code and oops.
Okay.
Okay, let me get to VS Code.
Okay, no problem.
Yeah, I'm coming. Okay. Let me share the screen. Okay. You can see my screen, right?
Yep, I can see it.
Okay, good. I'll be with you in a minute. Okay. Okay, before I say this, or before I continue, let me say this. You know, basically, an algorithm is a step-to-step way of doing a particular or solving problems, right? It
Right.
could be, for example, when you look at mathematical problems, each of the topics in math has its own formula through which you solve a particular problem under that certain topic. Is that true?
Right. Yep.
Hello?
Yep, that makes sense.
Okay. Let's assume that we have an array of, okay, let's say of alphabets. Okay.
Okay.
Okay. And we actually basically want to go through from A to E. All right.
Okay.
Big O, the first rule of big O is you need to determine the worst case. Like when you check the graph, okay, or when you check the big O cheat sheet, you basically notice that both the time and space complexities, they talked about worst case. Okay, because at best, any of the algorithms or data structures could perform better. But when you look at the worst case, which of them, sorry, let me go back to that. Okay, when you look at the worst case, let me share the screen too. When you look at the worst case, like for example, for that of array, you find out the, okay, the worst case in deletion is O of n. All right.
Right.
Space complexity is O of n. Okay, but when you look at okay, we've actually looked at binary search tree. You now see the worst case too is O of n and O of n. But when you look at singly linked and doubly linked lists, the worst case it's at O of 1.
Right.
Okay.
Mm-hmm.
Is that right?
Yep.
Okay, good. So at this point now, when you compare the worst case of an array and that of any of the linked lists, either the singly linked list or the doubly linked list, you now find out that at its worst case, at their worst cases, the linked list, and any of the linked lists, either the singly or the doubly linked list, performs better than that of array at their worst cases.
Right.
All right. So the first thing you consider is the worst case. Moving back to my VS Code. In this our array, the worst case is A, because when you want to iterate through this defined array, let me just label it array. I know it's okay, I know array normally shouldn't be,
right,
but let me just call it array 1.
gotcha.
All right. When you look at our array 1, when you are going to iterate through it, before you get to our worst case is E at E. So you have to move through A, B, C, D before you get to E.
Yep.
Okay. So that's the first thing you need to consider. That's rule 1 in big O notation. You consider the worst case. Let me write a for loop.
Okay.
Okay. I is equal to array 1 the length sorry. Array 1 the I index of I. Okay. You can see the output, right?
Yep.
Hello, Tony.
Yep, I can see it.
Hello.
Yep, I can
You
see
can
that.
see the output.
Yeah, yeah, I can see it.
Before we got to E, okay, our program iterated from A down to E. That means our program used its memory to move to do this operation, right?
Right.
So our worst case now in this is finding E. So, and this is not all that efficient. Okay.
Okay.
Okay. The second rule is when you now have, our program on a normal day, there could be some other thing that could go along with this program or this code, right? For example,
Right.
like if I want to, let's assume that what I have here in array 2, there are numbers, all right?
Okay.
And I want to write a function that basically sums up the number. Okay. First of all, I will declare a variable. Let me say number and assign 0 to it. Okay. And I'll get a for loop. I've used I, let me use J.
Okay.
J less than, less than array 2 dot length increasing, sorry, I didn't close the bracket. Okay. Okay. So if I want to add the items on the indexes of array 2, what I need to now do is now to say plus equals num plus equals array 2 index j. Is that correct?
Yes.
Okay. Okay, good. Now, when this function runs, you now find out that num will only run how many times? Will only run once. Did you get it?
No, I don't get it. You said num only runs once? That's equals
Okay.
array 2j.
But when I call function, when I invoke function, the num will only run once.
Okay.
The other part of the program that will run repeatedly is going to be the for loop. Is that correct?
Right. Yep. But I see, because we're since we're saying num plus equals array 2j,
No.
that doesn't count for running?
No, that's within the for loop.
Oh, okay.
I'm not talking about within the for loop.
Oh, okay, gotcha.
Within the function body, outside of the for loop, it's only once that num will be created and the value 0 assigned to it.
Right. Okay.
Okay. So at this point, at the invocation of the function on whenever I call my function sum, and it's running as it's running from top to bottom. All right. When it gets here, this operation will only run once.
Right.
And when we get back, when you go back to our big O check sheet, remember it's the number of operations that will be done per time. Is that clear?
You said it's the number of operations that will be done.
Hello?
Yeah, you said the number of operations that will be done. You said behind?
Per time.
Yes.
Per time. No, per time.
Per time.
When
Gotcha.
this function is called,
okay,
num is going to run once. That's the number of operation.
Gotcha.
Okay, per time, per time. Each time I call sum, num will only be, okay. So now, when you now look at the for loop itself, it's going to run until this condition is met. And it simply means that we have 1 to 10 items within array 2. That means this iteration is going to run for 10 times. That's 10 different operations will run.
Right.
The for loop is going to run for 10 different operations. So the big O of at this point is going to be, let's use n. That's the number of the items that you have within the for loop.
Right.
Is that understood, right?
Yep, that's clear.
Hello?
Yep, that makes sense.
We are looking, what we are looking at now is the second rule to big O.
Okay.
Okay. So for you to now, for you to now get, hello?
Yes, I'm here.
Hello, Tony?
Yep, I'm here.
Okay, for you to now get the total big O analysis of this function whenever it's called, okay, you are going to sum the different number of operations that will happen within this. So if you are going to sum it now, okay, it's going to be big O, okay, at 1. We have 1 when the number is created, right?
Right.
Okay, we now have 1 plus big O of n. At the for loop, we have n number of times that is going to run. So we are now going to have n.
Got it.
All right.
Mm-hmm.
Hello.
Yep,
Good.
I understand.
Now, even if the number of items within array 2 is going to be 1 million, 1 billion, for example, Facebook app has over 2 billion users, right? So let's assume that we are going to run through the number of accounts that you have as registered Facebook users. So it's going to be, let's say 2 billion. It's going to be now 1 plus 2 billion users or 2 billion accounts or whatever that you have registered on as Facebook users. So you get that clear. So you now have the total number of the big O now, the total number is going to be 1 plus n. That is going to be the sum of this. There could be other operations that could run. All right. Now, but since we now have this, okay, and when you now compare 1, for example, if it's Facebook that you are the number of accounts registered on Facebook that you are iterating through, you now find out that you now have 1 which will remain a constant as long as this, whenever this sum is being called and it runs, 1 remains a constant. And when you now look at it, 1 in this place, it's our what? Constant.
Right.
Does that make sense?
Yep, that makes sense.
Good. Okay. And the second law actually says that we are to remove all constants.
Okay.
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 One. Okay. 2. Now, when you now remove the constants, this will now translate to become O of n. Does it make sense?
Yep, that makes sense.
Hello?
Yep, that makes sense.
So the big O of this function, whenever I call it, it's O of n.
Got it.
Is that clear?
Yep, that's clear. Quick question for you though.
All right.
So for with num plus equals array 2, we don't count that. We just count the once we get a for loop, then we only basically measuring the for loop, but not really what's inside, unless it was another for loop.
Okay, that wasn't what I said.
Yeah, I was asking.
You count every. Okay, you count every part of the program, and you sum them up.
Yes.
All right. You now use your initiative to check the one that remains constant, no matter how many times I'm going to call this function sum. Even if I call it for 1 billion times, as it's running from the beginning part of it down, when it gets here, this can only run once.
Right.
Is that correct? Let's
Yes.
assume we have another variable. Let's call it nums
Okay.
2. Okay. This is going to be the operation it will only run once. That's the number of operation as long as this sum is being called. Even if we have like 20 of them, okay. Even if we have some more, let's keep adding s to them.
Right.
All right. Okay. So now we have different operations here, and all of them are running only once. Each time this sum function is called. Okay, this will run once, this will run once, this will run once, this will run once. For us to now calculate the big O of this entire function, all right? This one, I just returned it. Okay, the return part of it will equally run, oh, sorry. The return will run once. Okay, now we now have 1, 2, 3, 4, 5. Let's add all of them. Okay, 4, 5. 1, 2, 2, 3, 4, 5. Remember, we are summing up the individual operations within the sum function.
Gotcha.
Is that clear?
Yes. That's clear.
Okay. So you now have 1 plus 1 plus 1 plus 1 plus 1. That's 1, 2, 3, 4, 5. Okay. You now have 5 different operations that will run at constant time. That is, that will run only once. We now have 5 plus 1. Is that correct?
Yes.
Good. Now remember, I can decide to add some. I hope you can see me, right?
Yeah, I can see it.
I've added some more items within array 2. I've increased it from 10 to 15. All right. Now this end will, okay, this for loop within some function is going to run 15 different times.
Right.
Like, remember, I used Facebook accounts, registered accounts on Facebook as a point of reference. And I said it could be up to 2 billion using Facebook as an example. Now you find out that at each point, for example, as we are discussing, I want to believe somebody somewhere within the world has registered an additional account on Facebook. It's possible, right?
Right.
Now you now find out that the number of the items within that array is increasing. Right? But this other declaration of variables and assigning values to them and returning of value, all of them, none of them is changing. They will only run once. That's the number of operations for the creation of these values is only once for each of the values. Now, that's why you now have all of them as O of 1. That's constant time.
Right.
No matter how much this array items increase or decrease, is not going to affect this declaration of and assigning of values to the variables. Right?
Got it. Yep.
Good. So of all these ones now, they have remained constant despite the changing value of the items in the array too. So when you now sum up all the individual big O's complexities for all the operations within the function, you now get this place. Can you see my cursor?
Yep, I can see it.
Hello? Good. You now get this.
Right.
You now get this. And when this is added, it translates to this, right?
Right.
Now, the big O second rule says, whenever you have summed up all this, okay, that you should remove the constant. Okay, let's quickly go back to our big O website.
Okay.
Good. Now, when we get back to it, hope you're there, right?
Yep.
Hello?
Yep,
Good.
I'm there.
When we now get back to it, we now find out that okay, for example, there are so many methods in an array in JavaScript, like you have the pop method, the push method, the shift, the unshift, and all that. Okay, you can use for loop to iterate through an array and all those operations that can be done using all those different methods.
Right.
Now, but you now find out that when we get to the graph itself, we only have O of 1, log n, O of n log n squared, 2 raised to the power n, and n factorial. Does that mean that these are the only operations that are obtainable in a program? No. There could be some other programs that, like for example, I believe you've been writing codes. When you declare a function, it may not contain only a for loop. It could contain some other operations and all that. You could have a callback function. You could have so many other things within a particular function. Okay. Now, when you sum up all those different operations, all right, when you sum them up, you can now get something like this. You now find out that irrespective of how many times you're going to call that function, some will just run only once. Like for example, if another example of anyone that is going to run at O of 1, it's if I want to get, let me assign, okay, let me just say console.log array, okay, sorry, array2. Let me grab an item at index 4. Hello, did you see what I just did?
Yep. Console.logging.
Good.
An item, yep.
Yes. At line 19, I'm assessing the item at index 4, which is going to be 5, right?
Right.
0, 1, 2, 3, 4, which is going to be 5. Now, this operation is going to run at O of 1. Okay.
Okay.
When this is being interpreted, when this code is being interpreted, it comes here, it declares this variable, it assigns this, it gets here, it does the same thing, it gets here, it does the same thing. When it comes here, it moves back, it grabs 4, and it prints it right at the console. When it gets here, it's not going to run once, it's going to run repeatedly until this condition right here, okay, is met. Okay. Once it turns false, it continues. But before it turns false, it simply means that this for loop statement is going to run this number of times. That's the n number of times. Right. Like we now have 15. So it's going to run 15 times. Right. Okay. Then when it gets here too, it can only return num once. Right. All right. Is that it? Like when you look at my console, you now find out 5 only ran once. The return value only came out once. Okay,
Mm-hmm.
but let me show you what I've been trying to say. Oh, sorry, that's gee.
Yeah.
Hello?
Yep.
Did you see that okay, this place, did you see that it ran 15 times?
Yep.
Here, down to here.
Yep, I see it.
Now imagine that, imagine, okay, let me do something. Array 3. Let's give it 20 and fill it with just letter A. Okay, and here we now change here to array 3. Then down here too, we change it to array 3. Oh, something. Array 3, new array. Okay, now you see, I replaced array 2 with array 3. You now see that I declared array 3 and assigned 20 spaces to it, right? And
Right.
asked the program to fill array 3 with A. Now, you now see the A's.
Yep, I can see it.
Hello?
Yep, I can see it.
Good. I can now increase it to 1,000. You find out the program will continue to run and the rest of them. And it will take a longer time for it based on the number of inputs it's going to get. Okay,
Right.
before any other thing. So you find out that this for loop here, the number of operations that is going to happen here is going to be determined by the number of inputs I give to it. Is that correct?
Right. Yep.
Good. That is this n that we have here. This n could represent, like, if you are using Facebook, it could represent over 2 billion registered users of Facebook.
Right. Yeah.
On Facebook rather. Good. But when you now compare this 2 billion or whatsoever value that this n represents, you now find out that these ones seem to be insignificant compared to it. They are constant, and this one can increase even up to the infinity. That's why you remove the constant, because these ones are not going to affect the sum number of operations that will run within this function.
Right.
Okay, good. So that's what you do. You now remove all the constants. And when you now remove all the constants, like if we remove all the constants here, we are now down with O of n. That's going to be our big O.
Right.
Good. Is that clear?
Yep, that makes sense.
Any question?
Nope, I think that's good.
Okay.
That makes sense.
All right. So we can continue, right?
Yep.
Okay. The third rule says that you assign different terms to different operation. Okay. Or you can say different inputs have different terms. Let me rewrite it.
Okay.
Different inputs have different terms. Okay. Okay, let me clean part of this. Okay, let me leave it and use another function. Sum 2. Let's assume we have a sum that takes in 2 parameters. Are you there?
Yep, I'm here.
Okay, we have we have a function sum2. It takes 2 different parameters, and these 2 different parameters, okay, are going to be, I'm going to use array1 and array2. Let me shorten the number of items in array2 down. Let me scale it down to 10. And okay, I'm going to use this will be the argument for this function sum2. Let's say we now have a for loop. Oh, let's use a better convention instead of
yeah.
Okay. Let's say is or less than array1. Okay. Okay, sorry, let's also let's declare another variable here. What would I call the variable? Another sum. Let's assign 0 to it. And here, what we'll just do is another sum. Okay, plus equals array1 at index I. Let's assume we have another for loop running here. Okay, less than array2, the length is going to give us this. And let's see, let's declare another variable here. Let's just say, what will they call it? Another sum, and assign 0 to it. Okay. Plus equals array2 at index j. Okay.
It looks like you're missing dot length on that first for loop. Where it says array1 and then dot length.
Okay. Yeah. Thank you.
No worries.
Thank you so much.
No problem.
Okay. Let's just console out the 2 numbers.
Okay.
Yeah. Let me give more space here. Okay, you may remember our array1 and our array2. You notice our array1 has a different array length, right?
Right.
Our array1 has about 5 different items in it. That's a length of 5. And array2 has a length of 10.
Mm-hmm.
Now, in this case, Okay, it says that different inputs have different terms. For us to get our big O, the total big O for this function, okay, we don't know what it is for now, but let's calculate the different operations that will run with whenever we invoke sum 2. Here is going to be O of 1, right?
Right. O of 1 there too.
Creating the variable and assigning 0 to it. Once this function is running, it's only going to, it will only run once.
Right.
All right, good. Then here too, the big O for here is going to be 1 constant time.
Mm-hmm.
Now, the big O that you have here is going to run based on the logic we applied here, is going to be based on the length of this array. Is that correct?
Right. Yep.
And we have the length of this array to be what? 5. But we can represent it with, let's use A here.
Okay.
Okay, good. Then 2, the second for loop. You now have a second for loop. The number of operations is going to be based on the length of this array. Is that correct?
Yep, that's correct.
Okay. So as it is at that point, that is what it is, different lengths. All right. Different array lengths. Array 2 has about 10 items in it. That's yeah.
Right.
10 items, and array 1 has 5 items. So, but our third rule says that different inputs have different what? Terms, because they don't have equal number of inputs, so they have different what? Terms. They have different big O's. Now, when you come down to console log these variables, these two variables, another sum spelled differently, you now have it will only run once.
Right.
Is that correct?
Yep.
Now, when we want to do the summation of the different parts, the big O's for the different parts or the different operations within this function, is going to be O of 1 plus another O of 1 plus O of A, sorry, O of A plus O of B plus another O of 1.
Right.
Is that correct?
Yep.
Good. So our big O now is going to translate to 1, 2, 3. You now have 3 plus A plus B. Okay.
Mm-hmm. We
now fall back to our second rule that states that we should remove all constants.
Right.
Then we throw away this constant. We are now left with O of A plus B. It looks strange, right?
Right.
Okay. Let me show you something.
Okay.
I'm going back to the big cheatsheet.com. When you actually look at all this, do you see anything that looks like what we just got?
Probably the n to the n squared.
No, we got A plus. Okay, let me go back. We got A plus B.
Oh, n plus k, I think.
Okay. Does n plus k look like 8?
Yep.
Good. So that was how here in bucket sorts, radix sorts, counting sorts, that's how you that was how they got something that looks like what we got.
Gotcha.
Okay.
Okay.
All right. So we've now gotten to how we get that kind of big O.
Right.
Hello.
Yep. Yep, I'm here.
Hello.
Yep, I'm here. Can you hear me?
Okay.
Okay.
Yeah, I can. So has it cleared that path?
Yep, that makes sense. This makes sense.
Okay. So that's it. Then you find out that when we move back to our big O cheat sheet, we've not actually looked at the one that looks like, okay, when you look at the graph itself, I'm at the graph now. When you look at the
Right.
graph, there's one that has
N squared.
O squared, right? Then you have 2 raised to power n, and you have factorial, n factorial. Though all these ones are horrible, nobody wants you to actually get this kind. But let me just give you one so that let me take 2, the O squared and n factorial.
Okay.
Because this n factorial is going to show you something. I will use it to, at the end of the day, describe something for you.
Okay.
Okay, let me move back to Visual Studio Code.
Okay.
Now, so by implication, when we have 2 for loops, okay, that are not nested, not nested, you add, or you sum, you add the complexities of the for loop. Okay. Let me bring it down to all these places, to where we have our rules. Yeah. That's what is obtainable under rule 3.
Okay.
Now, so what happens now when you now have nested for loop?
Oh, I think that may be where you get the n squared.
Good. That's when you get the n squared. Let me just show you. Like, for example, I will show you based on the number of operations that is going to run is so that we don't waste so much time on it.
Right.
Let me say nested for loop. Let's say I will still use exactly the same. Oh, okay. Don't worry. Let's see. Sum for this is 0. For let I equal to 0, I less than array. Okay, array. Which one has? Okay, let me use array 1.
Okay.
because it has letters or alphabets. Then inside of here, let's have another for loop. Okay, I keep missing this dot length.
Oh, yeah.
Array one dot length. Okay. Okay, let's say console.log I and j. Oh, sorry. Let me use array one index of I and array one index of j. Okay. Let me call nexted for loop using, let's say, x here. Array one dot, oh, sorry, array one. Sorry, let me check through the code.
Okay.
Accept for loop, accept. Okay, I guess, okay. Okay. It has printed, right?
Right. Yep.
It has printed.
Yep.
On your own later, so that we don't waste time.
Yeah.
Count the number of operation here. Okay, it's going to, what you're going to get is the squared of this. That's 5 times 5, that's 25. That's
Yeah.
what is going, that's what you're going to get
Gotcha.
here. Okay, so yeah, so here, oh yeah, it's there. So here, sorry, I didn't space my code well. My bad. So here you are going to have O of n, and you, since it's the same length, you're going to have O of n again. All right, it's the same number of array. So, or the same length of an array. So remember, except when the terms or the inputs are different, that's when you have different
Right.
good. But here you have the same inputs. All right.
Right.
So it's going to be, and because it's nexted for loop, it's going to be, we are going to multiply, you're not going to add, to nested for loop. You multiply the inputs. Okay.
Yep.
Okay. So these ones are just the side notes to that. Okay.
Okay.
Then rule number 4. Hello?
Yep, I'm here.
Okay. Whenever you have a question, don't hesitate to interrupt me. All right.
Okay. Sounds good. Yeah, it's all making sense.
Yeah. You said?
I was saying it's all making sense. I don't have any questions right now.
Okay. That's good. Then the last part of it says, the last part of the rule says that when you have non-dominant terms, you drop them. I said?
Yep, I'm here.
Okay. Now, for example, when you have a single for loop, like in this kind of situation, okay, I'm lazy, let me copy.
No worries.
Let me comment it out and copy. Oops, sorry. Assuming you have a code like this, okay? Remember the big O for this, we got O n raised to the power of 2, okay? So when you now have this kind of code and you have another, you have a nested for loop, okay?
Okay.
And you have another loop that is not nested. Let's take array 2.
Okay.
Yeah. Let's console the log of, let's console array 2 at index of, at index of key.
Yeah.
Okay. Sorry, I'm trying to, I saved before I finished the code.
Okay.
That's why it's throwing up error.
Oh, okay. No problem.
Yeah. Okay. Now, when you have two sets of for loops within a function, and one of the sets is actually a nested for loop, and the other one is a non-nested for loop. We had established that this for loop here, from our last rule, we had established that the big O is going to run at O raised to the power 2.
Right.
Is that correct?
Yep. O
Okay,
of n squared. Yeah.
Okay. Now we have another for loop, and this one is going to run at O of n. Is that correct?
Correct.
Right?
Yep, that's correct.
Okay. Remember, here is going to be O of 1. I hope you remember.
Oh, yeah.
Then here, oh, sorry, it's not going to be O of 1. It's going to be O of n.
Oh, okay. See, well, because we didn't, I thought if it was in the for loop that we wouldn't count it, but we count it if it's in the for loop too.
Yeah, it's going to run based on the number of inputs here, because it's still within the for loop. So the total is going to be this.
Okay, gotcha.
Good. Now, okay, before I proceed to rule 4, let me quickly point out this. Now that you have this, okay, this is going to run at this. Let me duplicate this. Okay, this first console.log is going to run at O of n. The second one is going to run at O of n. Is that correct?
Correct.
Good. So here, this for loop is going to run at O of n, but it's not really from the onset. It should be, let's solve it first. It should be, let's sum up these two, as in these two. Okay. You now have O of n plus another O of n. Is that correct?
Correct.
Good. Then we are now going to have 2n.
Right.
The factor of n is 1. So 1 plus 1 is going to give you 2n.
2.
Is that correct?
Yep, that's correct.
Good. And you know 2 of n simply means 2 times n, right?
Right.
Good. Remember our rule 2. It says remove all what? Constants.
Constants.
So these 2 will go, remaining n. That's
Right.
why at the end of the day, the big O for this for loop, despite the fact that you have, oh, sorry, I uncommented it. Despite the fact that you have this first console.log running at O of n and the second console.log running at O of n, the overall complexity for this for loop is going to be at O of n.
Gotcha.
Does that make sense?
Yep, that makes sense.
Good. So we've established that this runs at O of n. Okay. The nested for loop by our last explanation under our third rule, we agreed that it's going to run at n raised to the power 2. Is that correct?
Yep, that's correct.
Good. So since both of them are within this function, and this one is going to run at O of 1, right?
Right.
Good. Now, the overall big O here should be O of 1 plus n to the power of 2 plus n. We've not met anyone like this before. We've met something like this, and we agreed based on our second rule that the constant should do what? Should go.
Right.
So the constant has gone. All right, based on our second rule, we are now left with this plus n.
Right.
Is that correct?
Yep, that's correct.
Good. Now, since we are all now left with this, and we cannot add n to the power of 2 to n, what is going to happen? Let's fall back to our fourth rule. It says drop non-dominant terms.
Right.
If you look at these two, which one is going to dominate? When you have, this one is going to be to the power of this, right? This is to the power of this. So if this one is 2, if n is equal to 2, that simply means that n to the power of 2 is going to be what? 4.
Right.
Is that true?
Yep, that's correct.
Good. If n is equal to 10, that means that n to the power of 2 is going to be what? 100.
Right.
You now find out that n to the power of 2 as any input, all right, n to the power of 2 is going to increase larger,
Right.
okay, than n at any given number except for 1, because n to the power of 1, sorry, 1 to the power of 2 or 1 to the power of any number remains 1. But anything beyond 1, okay,
right,
n squared is going to dominate.
right,
And n is not going to dominate. Let's take, for instance, let's go back to okay, for a social media app like Twitter that has about, I think the last time I checked, it was about 360 million users on Twitter. Let's assume that, okay, the number of users on Twitter, n is equal to 360 million, right? And
right.
n to the power of 2, of course, you know, I don't even know.
Crazy.
Good. So you know what it's going to look like when you're going to compare 360 million to 360 million to the power of 2. It simply means that n is a non-dominant what? Term.
Right.
So from our fourth rule, we simply state that drop the non-dominant term, which is n. So the big O here is going to fall back to n to the power of 2.
Right. Got it.
Okay.
Yep.
So that was how. Okay, let's move back to our big O site. That was how all dates, okay, all dates were established. I know we did not touch every one of them,
right?
But as time goes on, we will touch the basic ones that are left now. Log n, log n, and 2 to the power of n. This exponential, but I think this one is too crazy. We can just let it be.
Right.
All right.
Okay. Gotcha.
Good. This one, this log n should be our focus.
Okay.
Okay. So let's take log n and n factorial. I told you I'm going to show you something about n factorial. Okay, and I'll use a code to show you. Let me open a developer's tool. My developer's tool. For example, okay. Oh, just clear. Okay. I'm being asked, okay, to find to find 5 factorial. All right. That's okay. Okay. Now, you know, in JavaScript, there are so many ways that you can do a particular thing. Is that true? You can solve a particular problem. Like, for example, I can, you know recursion very well, right?
Yes.
Good. I can use a recursive function to actually find 5 factorial, and I can equally use a for loop to find 5 factorial. Let's just look at the two of them. Okay. Okay.
I'm not really good on recursion yet, but I understand it though when I see it.
Okay. Don't worry, we'll get to that. Okay. But just follow me. Just follow me. I just want to establish something.
Right.
Okay. Okay. Now, when you just follow me, don't worry. We'll focus on recursion. We'll treat recursion separately as a topic of its own, so that we look at it. All right. But for now, just follow me. Yep. When you now see the A is equal to, is less or equal to 1, let's say return 1. Return. Of course, basically, you know that recursion is actually a function that calls itself, right? Right. Good. So.
And then the returning 1 would be the base case, right?
Good. So if I call this, if I call this using 5, okay, it has given me 120. Is that correct? Yeah. Okay. Let's use for loop. Let's use for loop to solve the same problem. Let's just assign a number 1. Okay. Okay. Yeah. Then write our for loop. I is equal to let's say 5. We can start at 5, or we can even start with Let's start with 1. Okay. For I that is greater or equal to 5, let's increase our I. So we can now say num, okay, is this times I. Oh, I did not console.log. Oh, sorry.
No worries.
Let me recopy. Let me
Okay.
recopy it. Sorry, don't mind me, because I think if I press enter, it's going to what is it called?
No worries.
Let I equal this and this equal this greater or equal to this. What happened? Sorry, let's go to VS Code.
Okay.
Oh, don't worry. Let's rewrite it from start. But you've gotten the concept of recursion, right?
Yep.
Okay. Let num equal to 1 for I greater or equal to 5. Okay. Less or equal to, shouldn't be greater, it should be less.
Gotcha.
Yeah. Then num multiply by I. Okay. Console.log. Oh, let me return at the end. Let me just return. He gave us the same thing, like let me say, let's say fact 5 x. Oh, sorry about that.
No worries.
If z is of less or equal to 1, let's return 1, or else return z multiplied by factorial z minus 1. We have the same answer, right?
Yep.
Okay. Now, based on big O from the way we've actually gone through it on VS Code, here we are going to have, in this for loop, we are going to have, 5 operations, right? Which is going to be O of n. Is that correct?
Yep, that's correct.
Good. But do you know how many operations that we are going to have here?
How many is it?
Don't worry, let me show you.
Okay.
is going to run multiple times. That's why is somehow a trick, but I'll show you that's why recursion is actually not a good method for solving problems. They play in a place like if you've gone for an interview, because it's the big O is at
it keeps calling.
n factorial, n factorial. So it keeps calling. I've missed something. That's called. I want to actually use a debugger so that we examine it and see exactly things, what is happening in between. Okay, before I get to you, let me call it debugger first. If x is less or equal to 1, return 1, then or else return x multiplied by factorial x minus 1. Okay. Let's now call it. Let's give it 5. Now watch. Watch what is going to happen at the stack. Under call stack. Remember, we have called it. Is that correct?
Right. Yep.
We had called it once. Now, but it's pausing at this debugger. This place is highlighted. Now, let's ask it to step over.
Okay.
It says, be watching under this call stack.
Okay.
What will be happening? It has called it again. This is the second time. Okay?
Right.
Let's go again. It has called it the third time.
Yeah.
All right? Let's go again. If I press this, it calls it the fourth time. Let's go again. It has called it the fifth time. Now, x is now equal to 1. So it cannot bypass this return because this condition here has been met. It will now finish. Now, watch what will start happening at the call stack. As we are stepping over, it's now removing the functions from the call stack. Now, did you notice at the end of the day, it has given us, what's it? The total value, the answer, 120.
Right.
But if you do exactly the same thing, if you do exactly the same thing for our for loop, you find out that you will not get, or the system or the device is not going to use up such resources to call this function those number of times that the recursive function will call it. So that's why, what is it called? The big O at this is at n factorial. It uses both space and time before it gets the answer. The problem is not now, the problem is not getting the answer. Both methods will eventually give you the answer, but one is faster and the other one is actually, one is faster and doesn't use so much memory space, and The other one uses more memory space and is very, very slow. That's why in an interview, if you are being given a problem that you can solve with both recursive function and a for loop, rather choose to go for the for loop instead of recursion. Or you could be asked, why is recursion such a bad solution?
Right.
It's because it uses up memory space and it's slower.
Right. Gotcha. Perfect.
All right.
Yep,
Yeah.
that makes sense. Very awesome.
So that's it. That's why this recursion, that's why it's a very bad idea.
Gotcha.
Good. Then when you now talk about log n, I had shown you log n, but it's just that you did not realize that you've actually met log n. Can you remember what I did on the whiteboard?
Yeah, the binary search.
Good.
Mhm.
The binary search uses log n.
Mhm.
Okay. Let's go. Oh, let me see if I can find a whiteboard.
Okay.
If it hasn't wiped. Okay, but you know exactly what we did. Okay, good.
Yeah. Mhm.
You know exactly what we did. We
Yeah.
have about 1, 2, 3, 4, 5, 6, 7 items in the array. All right.
All right.
Okay, it's not even. Let's make it 8. Had it been that we had like 8, let's give it another one. Let's make it 8 now. Don't mind me, please. It's just because of space.
Right.
But
Yeah. No,
I
no problem.
believe you will understand what I'm trying to
Yeah.
say. Good. Now, if you apply the same method that we had applied initially, oh, sorry. If you apply the same method that we had applied, you now come to the, okay, 2, 4, 10, 17, 15, 73, and AC.
Mhm.
Now, 1, 2, 3, 4, 5, 6, 7, 8. Okay. If you apply the divide and conquer method, and we are looking for, let's say we are looking for 50, okay?
Mhm.
If you apply the divide and conquer method, remember the divide and conquer method will actually will split this array into 2 equal parts, so to say. All right, but sometimes you may have the length of an array to be what do they call it? Not to be an even number, but to be odd. All right. Okay, but whichever way, it could still work. But let's assume that now that the length of array it's an even number, not an odd number. Now, and we are looking for 50, right?
Right.
Good. As we are now looking for 50, what will happen is when we actually apply divide and conquer method, we now have split these items in the array into 2 equal parts, the left side and the right side. And we now check, and we are looking for number 50, right? And we now check the maximum number on the left-hand side, it's 10. And when you compare 10 and 50, 50 is greater than it. That means 50 cannot be found this way. Is that correct?
That's
good.
correct.
Then we now split this array and now focus on the right side.
Right.
Good. Then we come down again. we are now going to be left with 17, 50, 73, and 80. We apply the same method again. We apply the same method again by dividing this into 2. Okay.
Right.
Once we split it into 2, we now check 50. This side is greater than 50.
Right.
All right. But this side is equal to 50. So we cannot discard this side and now focus on here.
Right.
Okay. Then we are now left with 17 and 50. And we apply the same thing again and now check 50. We've now gotten 50. Is that correct?
Yep. That
So
makes sense.
from this, we've done how many operations? 1, 2, 3.
Yep.
Is that correct?
Yep, that's correct.
Okay, I want to wipe all this.
Okay.
Okay. I should go ahead, right?
Yep, you can go for it.
Okay. Okay, remember the length of array was how many?
8,
Good. Okay, and we did how many operations?
3.
Okay, so 3. And when you look at log base 2, when you look at okay, this simply means that 2 to the power of 3 will give you how many?
8, yeah.
Is that so? Sure.
Times 2, 4, times 2 to 8. Yep.
Okay, good. I wanted it to be sure. I know it's 8.
Yep.
Yeah. Now let's do something once again. Let's move over to chat sheet or cheat sheet, sorry.
Okay.
You notice here it's to the power of how many? 2, right?
Right. Yep.
But here, when you now apply this, let's go back to our whiteboard.
Okay.
When you apply this, you now find out that it's equal to, remember, sorry, let me wipe this. Remember, in the array, okay, the array has how many?
8.
Good. And the number of operations we will do to get the last item in the array is how many?
It was 3.
8. In the array, we iterate from the beginning to the end. So for us
if
to
you go
get
from the beginning to the end.
last, for us to get to the last,
Oh, okay.
we have to do 8 iterations or 8 operations, right?
Yes.
In an array. Fine. But in binary search, we had 8 items and we did how many operations?
3 operations.
Now, when you now want to now scale it down from this to this, how do you get it? When you do the inverse of square root, sorry, the inverse of this,
Yes.
mathematically, you get the log of this. Is that correct?
Okay.
Is that correct?
I believe so. That I didn't know.
Don't worry, when we get to binaries, if we are going to do binary search, when we get to
Yes.
binary search, okay?
Yes.
But for now, I know it may not be that clear.
Right.
All right. But you can check the
Yes.
the log function is actually the inverse of the
Gotcha.
square function. You can check. But when you want to actually get it rightly or do the derivation, it will be easier when you have a tree. Okay. When you have a tree, when you now look at the tree and run it down, you can now get the logarithmic value of the n. So at the end of the day, what I'm just trying to pass is, at the end of the day, this log n is the inverse of this.
Gotcha.
That's why it's tending to this way, and this other one is tending to this way.
Gotcha.
Okay.
That makes sense.
We have now covered the basic ones. Let's leave the exponential for now, and let's leave the n log n. And let's just focus on the linear time, the log n, and the O of n. We've seen factorial or recursion, and we've seen why it is a very bad idea.
Right.
When it comes to using it as a means of solving an efficient problem, recursion is a bad option.
Gotcha.
Good. Then we've seen the quadratic, that's n to the power of 2, and we've seen this and we've seen this. Okay, I've been talking too much. Let me be quiet and listen to you. They said that's the way you communicate. Yeah.
It makes sense. It makes sense. I think now just maybe practice for me.
Okay. So basically, this is what we have as the foundation. So now let's scroll down.
Okay.
Yeah, so I believe we are not going to take everything today, but we'll gradually take it one after the other. And as you're taking them one after the other, you understand, you start seeing the efficiency part of it.
Right.
We are not going to build any project, but when you now look at, okay, why do you have to build a stack or a queue? You now look at it. Okay, first of all, you have an array. The way I would like us to take it is going to be array. Okay. Hash table. Then stacks. Okay. Linked list. Let's go with linked list first, and we can now look at stack and queues. Then we look at graph. They said trees. Three data structure is a type of graph data structure.
Okay.
All right. Yeah. So I may not say tree and graph. Let me just say graph, because tree is a type of graph. So when we go that way, you begin to understand why search. Okay. We've done, if you've been very, very careful listening, we've actually explained why search is O of n.
You said we have explained that?
Yeah. I've explained that. Worst case, trying to get the last item on the array, that means you have to start from index 0 till you get to the array length minus 1. That's the last index of the array. So for you to move
Facebook with their billions.
Good. That means you have to do 2 billion plus number of operations. So for you to now go from 1 to the last item, think about the resources that your device must have used to do that kind of operation, and it's not going to counting from 1 to 2 billion, not just not just billion to 2 billion plus.
Right.
That it's going to take time. But you now ask yourself, why is it that each time I do a search operation on Facebook, I get the answer as soon as possible, like in a matter of seconds?
Right.
Good. So by the time we now begin to take this data structure one after the other, you begin to see why. Okay, you are good with array. You told me JavaScript is your first love when it comes to programming language, right? Yeah.
Yeah.
Good.
I like Java though too. I like Java as well. It just keeps me on my toes.
Java is very strict. Okay, you
Yeah.
need to specify everything you want to do, not like JavaScript that is dynamically typed
Well,
language and you keep going. Yeah.
Yeah, I like Java because it helps me understand what's happening, basically.
Yeah, it does. It does. In as much as for example, when you don't have the freedom to do some kind of things,
right,
basically, that you can that you do and get away with in a place like JavaScript, like you can declare an array and you can increase the size at will. Of course, Java is so strict that you dare not try it. Even if you do, it throws up error.
Right. Yeah.
Good.
Exactly.
So it keeps you restricted to certain operations. So you begin to understand, when, if you're like me, when I learned of programming, okay, there are some things that were not really explained to me that could happen under the hood. So, but when we actually look at arrays, we look at some little things. There are two types of arrays. You have the dynamic arrays, like you can see in JavaScript, you can see in Python. All right.
Right.
And you have another type of array they said is static arrays, like you have like in all those statistically typed languages like Java, DCs, and all that. So you understand why inserting an item into an array is going to be at O of n. It's a single operation, right?
Right.
You're just dropping something. It's just like a container. An array is just like a container. You're just picking a single thing and dropping into it. Why will it do some kind of iterations that is going to do as if it's searching for like the last item? Okay.
Yeah.
When you understand that, that's why I said understanding big O will play a very important role to helping you to understand these data structures, the operations, and the algorithms and their efficiencies.
Right.
Good.
Awesome. Well, that makes sense.
Usually what used to happen is when somebody wants to teach you data structures and algorithm, and the person starts teaching you data structure first and moves to algorithm, you may not really understand so many things that are happening as a result of not having that foundational knowledge of big O.
Big O.
So that's why sometimes you hear some persons will tell you, oh, yes, the true truth is algorithms have complex logic. I agree with that. But when you start understanding from ground to up, it will help you grow faster than somebody just lifting you and leaving you.
Right. Yep, that makes sense. Shoot. Well, that's good. I appreciate this.
You're welcome.
So
okay, I'm listening.
I was just gonna say, so when are we? You want to do daily or?
Which one do you find? Which one is suitable for you?
Yeah, if we could do daily, that'll be fine for me if you have the time.
See, my kind of my hands are tied. Some sort of. I told you I work, right?
Yeah. Mm-hmm.
I do 8 to 4,
Oh,
and by
okay.
the time I come back in the evening, I may have
Right.
some meetings to attend, then
Yeah.
come back, try to attend to myself, and do one or two things. Then read, because okay, I didn't tell you, but let me just tell you,
Mm-hmm.
I never had a CS background.
Oh,
Okay,
okay.
I entered into this because I have some kind of personal interest into it. By
Okay.
academic training, I'm a biochemist. All right.
Okay. Okay.
Yeah. So I'm a
Awesome.
biochemist. So I love reading,
Mm-hmm.
and I keep reading and keep exploring and keep learning. Nobody
Right.
knows it all. Like, for example, algorithm is too vast, but
Right.
you learn what you can per time. So
Right.
sometimes I need to go for meetings, and during weekends I need to do some personal studies
Right.
against Sunday, because most of the Sundays I teach. Okay.
Okay.
Yeah. So that was why I, like, when I remembered I didn't tell you about weekends, I now told you Mondays to Fridays. Let's
Right.
let weekends be
Yeah.
Saturday and Sunday, because I need to read, I need to study, and I equally need to, I'm not yet married, so I need to take care of myself, do
Right.
some cleanings and all that, and prepare for the coming week and all that for work.
Right.
So that's why, if you can just let it be Mondays to Fridays, for me, I think it's okay. Except if anything comes up in between. For
Yeah.
me, from my own end, as much as I will try to keep you updated, if anything comes up within the day that
Right.
may not make our meeting to be possible, I'll try to keep you posted.
Okay. Sounds
Yep.
good. Sounds good. I'm thinking, because even for me, every single day might be tough, because so I run my own business and stuff too.
Okay.
But I figured that some days maybe you could just say, hey, maybe like a homework assignment, you know what I mean? Where I could just work on it, something. Um, especially on those days, where you're not available.
Okay.
Yeah.
It's okay. It's all for good.
Okay, awesome. Well, thank you very much. I
You're
will
welcome.
see you tomorrow then.
Okay.
All right, thanks a lot.
Okay. So the payment, how do we go about it?
Did you want me to do like once a month or twice a month, or how often?
Which one is suitable for you?
I could do either one. So I mean, we could start off at twice a month if you want. Um, do you? So I have like Remitly, but I also have like crypto as well.
Mm, okay. For now, I don't do crypto.
Okay,
Yeah.
gotcha.
Mm.
What part are you in of what country are you in? Nigeria? Or
Is that?
what country are you in?
I'm in Nigeria.
Oh, you're in Nigeria? Oh, okay.
Yeah, I'm in Nigeria.
Okay, cool. Okay, well, cool. I'll yeah, when it's time I'll send it through. It's called Remitly. And to like you could send to the bank stuff.
Sorry, I didn't get it.
What was that?
I didn't get what you said.
Oh, okay. I was just saying that I can do it twice a week twice a month, and through a app. It's called Remitly, like remittance. Have you heard of that?
No, no. In our own kind of world, there are a whole lot of things that you don't have access to on the net.
Right.
Yeah, yeah. So basically, what do they call it? For me, I just have an account.
Okay.
Yeah, a bank account.
Okay. I'll ask you for the info then on WhatsApp because
Okay, I'll send it right away.
okay.
Yeah.
Sounds good. So let's see.
Okay. So we did 2 hours that like, oh, it shouldn't be up to 2 hours 30 minutes. It should be 2 hours 20 something
Right.
minutes or thereabout.
Right.
Yeah. So some days could it stretch, or we should let it stick to 1 hour?
I probably let's just say that if we're not gonna do the next day, we could just do 2 hours, maybe one day. But 2 hours is kind of hard because I have 3 kids and then I run my own business and stuff. So I'm usually like really busy. But so I do like the hour, but you know, if you're not gonna be available the next day, maybe we can do 2 hours or something.
Okay, let's see how it goes. Like I said, for now, Mondays to Friday, except on condition if nothing comes up in between.
Right.
But if anything comes up in between, I'll just have to let you know.
Okay.
Okay. It's
Sounds
going
good.
to be from any of the ends, either from your end or from my end.
Yep.
Yeah. So,
Copy.
but the only thing is, however it happens, the other person should keep the other person posted, at least if it's as much as possible on time.
Mhm.
Yeah. Why I been sending you notice like, okay, like 20 minutes to the time or 30 minutes to the time, it's because I like, okay, we have already had an agreement of time.
Yeah.
You understand? So it's just like, okay, a reminder that it's almost time. But
Yeah.
if it's not going to hold as much as possible that anything comes up, if it's like early enough,
Yeah.
the notice should
Just let you know.
come so that the next person shouldn't be waiting.
Yeah. Okay, I'll make sure. I got to set my alarm and all that. I'll make sure that I'm on though at 12 here.
It's okay.
All right. Well, I appreciate it. Then I'll hop back on with you tomorrow then.
All right.
All right. Thank you very much.
You're welcome.
Okay. Talk to you later.